This is a diagram of the OpenGL 4.2 pipeline. And if you've used OpenGL, you know that there are a ton of options, right? You can turn textures on and off and make them do this and make them do that and check for this and check for that. And that's what all of these little switchy things in here are. And OpenGL has to do that whether you're doing it or not, whether you're using that feature or not. And so one of the premises behind Vulkan is you don't have that. Is whatever you need to use, you put in your Vulkan application. Largely, you put a lot of these types of things in the shaders. Okay, the shaders have been really beefed up in Vulkan. Okay, so this kind of complexity, and the bad news is, you can't do these things just with a simple call like in OpenGL, but the good news is you get more performance because probably 90% of that are not things you use in any particular application. And why is it important to keep the GPU busy? Well, you look at things like this. How many CUDA cores are there on graphics cards these days? The answer is like 5,000. So one of the other trends in graphics, of course, is GPUs keep getting beefier and beefier. And so if you have a GPU and you can't keep it busy, well, why did you get the GPU in the first place? Vulkan is really designed to keep your GPU busy. That's part of its premise. All right, who is the Khronos Group? Now, we have the Vulkan swag over here, and I keep saying compliments of our friends at the Khronos Group. Khronos Group is an industry-wide standards organization. These are the standards that they currently oversee, and of course there's ones that we all know. There's Vulkan, WebGL, OpenGL, OpenGL-ES, and so on. This is what they do. And companies join this, and then they develop a standard under the auspices of Khronos. And there are a lot of members in Khronos. If you got a favorite, this is like playing Where's Waldo. Look here, ooh, Oregon State. I joined the Khronos Group, as this was one of the ways I decided I couldn't find another way to try and keep up on the standards other than joining the group that was working on them. But that's who Khronos is, and they oversee Vulkan. Who's been specifically working on Vulkan? These are the companies and organizations that have really been the most involved with Vulkan. And one of the interesting things that you'll see if you look at that is it's not just hardware companies. Well, sure, there's NVIDIA and AMD and Intel and ARM, but there's also software companies in here as well, like Unity and so on. Vulkan was developed as much by software companies as hardware companies. They all had the same goal: let's crank up the performance. And if you're a game engine company, this is really important. And so we have not just hardware people, but software people as well to thank for the standard. All right, kind of a quick history of Vulkan. It was largely derived from AMD's Mantle. AMD had what they thought was a better graphics package going at the time called Mantle, and its goals were pretty much the same as Vulkan. And AMD, to their credit, gave Mantle royalty-free to the Khronos Group and said, here, use this as a start for Vulkan. And so, thank you, AMD. I'm sure Vulkan is way far along the way, more than it would have been by then. It is, though, very much, it has learned a lot of things from Apple's Metal and Microsoft's DirectX 12. So, if you know those standards, you'll see pieces of them in the Vulkan philosophy. A goal was they wanted much less driver complexity. Well, it depends where you think of a driver as living. They moved it into your application. But that means writing a driver is much less complicated than it used to be. You didn't have to do all those switches and tests like you saw in the OpenGL diagram. Much less user handholding. All those tests in the OpenGL driver, well, they come with a price. The price is performance. It takes performance, even if it's just an if statement. Test to see if alpha equals 0. That's an if statement, and that gets executed every time you go down through the driver. Okay, let's get rid of that. Let's get rid of the user hand-holding. Let's not check if the user has the right number of bytes in their texture. Now, that's the good news. The bad news is you can crash Vulkan. Vulkan does not test for those things, at least not by default. And so, yes, you need to know what you're doing, but that's what we're all doing here this morning. OpenGL, most people don't realize that OpenGL is single-threaded only. The graphics goes out through one thread. You can have multi-threads in the application part, but the graphics goes out through one thread. And that's a real limit these days. OpenGL was developed 20-some years ago. That wasn't a big deal. There was no multi-core. Now everything is multi-core. So of course we want Vulkan to be multi-threaded, and it does. It has a lot of good constructs to take advantage of multi-threading. We're not going to talk about this, but this is important if you're on a mobile device. Vulkan can also do the tile render. That is, if you want to do a really beautiful screen or scene, you can tile it and then assemble the tiles. All right, Vulkan differences. I'm assuming everyone who's here knows something about OpenGL, and most of you have probably been using it for decades. So let's talk about some differences. Again, most low-level information needs to be supplied by you. Okay, and we'll see how that happens. The screen coordinate system is Y facing down. I'm not sure why. I'll show you why we care and how you just get around it in your application unless you really want to take advantage of it. There's no current state. OpenGL has a current state. The current state is sort of set in one big data structure, and then you have many, many copies of that big data structure so that you have, well, multiple states that you invoke at different times, but it's not state in the OpenGL sense. In OpenGL, we talk about things being deprecated. When it's printed that way, it's a nice, soft, deprecated. Well, that means things like GL rotate F, translate F, you don't have to worry about your own matrices. That's been deprecated in OpenGL, but it's not gone away. That deprecated in the OpenGL sense means it's just not recommended. In Vulkan, those things are deprecated. They are gone. Okay? You have to do all your own matrices. You have to pass in the matrices into the shaders. Okay? Now, it turns out that's not that hard, and there's assists to do that, and we'll look at that here. Yeah, you manage your own transformations. Also, one of the things that I think we'll all end up liking eventually is shaders are half pre-compiled. In OpenGL, when you run it, your shaders get compiled by the driver. In Vulkan, you compile the shaders into kind of an intermediate code, and then you include that intermediate code when you run your Vulkan program. Again, we'll look at what that really means. All right, here's why it's great to have quick reference cards. Vulkan is doing so much stuff that when I have a function like this, so say create buffer, it needs a whole bunch of arguments. And rather than put 20 arguments out there in the Vulkan function call, what they do in almost all calls is they have a structure. And so this is a type def for a structure, and then they set variables into the structure. And then they pass the structure into the function call. And this is why those quick reference cards are going to be so valuable, because it is impossible for any human to remember all of this. The good news is you don't have to. You've got quick reference cards, and you've got these notes. But you'll see this over and over. So again, if you've just come in, over on these chairs are some Vulkan quick reference cards and other swag. You don't have to dash over now, but at least at the break, be sure to get them. There's also nice diagrams in the quick reference cards. All right, when Vulkan uses its own terminology, this is the terminology it uses, and there can basically be any number of anything, all hooked together. Now, typically, your application ends up looking like this. You've got an instance of your application, you've
got a physical device, well, you might have multiple graphics cards, but typically you don't. Typically you have one physical device. That physical device can get broken up into logical devices. The logical devices are basically a way of buffering your code from the hardware. Okay, so logical devices are basically virtual things, and all of your graphics stuff gets put into command buffers. Again, we'll see this coming up, which go to queues, and then the queues get executed. This is where the multi-threading comes in. It's because you can have multiple threads all generating different command buffers, and then you flush them into the queues and graphics happens. So this is a good thing, and we'll look at that. Synchronization, I ought to mention real quickly, Vulkan does no synchronization. You'll hear me say this over and over. Vulkan wants to run flat out. Okay, you say, I want to do this. And if the next thing depends on that other thing finishing, that's not going to happen. And it's the next thing you say, and do this, is just going to run also. And if the first thing needed to produce something for the second thing, well, that's not going to happen. And so there's a few ways of doing synchronization in Vulkan, and you have to do it yourself, because only you really knows what your application looks like. Here's a real quick thing on the shaders. We're going to cover this in more detail, but this is a good summary. The good news is it's GLSL. And while the Vulkan development was going on, I was scared to death that they were going to do something totally different, thus obsoleting thousands of shaders that all of us have already written for OpenGL. They didn't. It's still GLSL, but there are some differences. And in the Vulkan compiler for GLSL, they've built in a pound define. And this is great, because now you can take your GLSL shader, and where there are Vulkan specifics, you can put in pound if def, and where there are OpenGL specifics, you can say pound not if def, and off you go. And so the 90% of the shader code that is common to both, you don't have to change. I really like that. Here's the part about compiling. So if your GLSL source comes to an external compiler, which we'll talk about, and that produces an intermediate format called SPIR-V. And SPIR-V, you can look at it there, you can disassemble it. It's just kind of junky looking. But that's what then gets read into your Vulkan program at runtime. And it does the rest of the compile. And then that's what your shader is inside your Vulkan program, because it's vendor specific. Now, why do that? And here's the real advantages. First of all, if you think of your shader code as being cool and proprietary, you don't have to release the source code. You release this SPIR-V format, and it's very hard to turn that back into shader source code. Your programs launch faster because half the compile's already done. This guarantees a common front end. That is, we all know that some vendors add extra features into their shader compilers that don't work on other vendors' graphics cards. And also, this allows for other language front ends. That is, you can write a Python shader language if you want, just as long as it follows the SPIR-V standard for what the assembly comes out looking like. So this is cool. Again, we'll spend some time on this because this is something we all have to know. All right, so if you go to that website, and I'll put the website up again later, one of the things you'll see in there is some sample code. And it's in a Windows zip file, a solution file. It's got everything you need in there, all the .h's, all the .cpps, all the libraries, everything. And so in theory, you just double-click on the solution file, and off you go. Now, it's Windows, and that's what's out there. But one of the cool things about Vulkan is it really can run in lots and lots of places. It can run on Macs, it can run on Linux, it can run on mobile devices. So just because this is a Windows zip file, don't get the impression it can't run other places. It can. All right, so that's kind of the introduction. Now, normally when you take a graphics class, you start at the beginning and you say, well, here are the libraries you need to link in, and here's how you set everything up. And I know from doing this with college students, they hate that because that makes it like 2 weeks till they can see a pixel on the screen. And that's very demotivating. So we're not going to do that. We're going to start with how do you draw something? And then later on, we'll get to how do you set it up, okay? And also the other reason for doing this is I want to reassure everybody here that when you draw using Vulkan, it doesn't look that different from drawing using OpenGL. It's the same kind of vertex buffer stuff you may have gotten used to in OpenGL. Yeah, begin, end are gone in Vulkan, but vertex buffers are still there. So the first thing we're going to look at is a Vulkan data buffer. Okay, that's not really drawing something, it's storing something, but vertex buffers are a special case of data buffers, so we might as well start with data buffers. All right, a data buffer is just a bunch of contiguous bytes. There's nothing special about it. Vulkan being Vulkan, it's not going to test to see if it's in the right format or if your floating point numbers aren't reversed. It doesn't care. It's just, well, what some people call a blob, a binary large object, okay? And so you can store anything you want out there. It doesn't have to be vertices. In fact, we store lots of other stuff out there. And Vulkan calls these buffers. You'll see diagrams like this throughout the notes, and I'm not going to talk about them, but they're here for the sake of completeness. Because of all this emphasis on data structures, a struct here holds this information, and it gets read in there. What you'll find, and I ran into this when I was trying to teach myself Vulkan, is there are structs that plug into other structs, that plug into other structs, that finally plug into the function you were trying to call in the first place. That's what these diagrams are meant to show. Okay, so they're there for the sake of completeness. So here's how you create a data buffer. Let me start down here. VK create buffer. Vulkan functions begin with a lowercase v, lowercase k, all of them. Pound defines begin with capital V, capital K. And type defs, I don't see any here. Type defs begin with capital V, lowercase k. Again, you'll get really used to that after a while. All right, there's a type of struct called buffer create info, and here's what goes into it. Now, throughout the sample code, if you go look at the sample code, there are places in there where the code, when it's setting an option, it actually comments what the options are. One of the things, and I guess I'll apologize now and I'll apologize later. If you look at the sample code that comes with this, it is appallingly verbose. It is much bigger than it ever needs to be. But the reason is, I think when you're learning something, you get very tired of example code that uses shortcuts. Okay, here's a structure, and it was defined somewhere else. Good luck finding it somewhere else. Oh, and here's something, and I'm using my little C++ helper function here. Good luck finding that too. And so in the sample code, it, again, is appallingly overwritten. But the idea is that anytime you need to see something, you say, where did that come from? It's not far above it. And so that's why sometimes the sample code will just list what some of the options are. And that's the type of buffer you're creating. Okay? Here in the struct, you're setting the buffer size. Anytime there's a size, it's always in bytes. Again, it doesn't care about the structure of what you're storing. It only cares about, well, they're bytes. Okay. Here's what kind of buffer you're storing. By and large, I don't think that matters much, but I suspect there are some Vulkan drivers that will look at what type of buffer you're storing and will make some optimization changes based on that. Okay, and so it's best to say what you really mean. So for instance, since we're doing drawing, we're going to say we're using a Vertex buffer. And then you finally make the call. In the sample code, the sample code, and what we'll see in these notes, you'll see every so often a capital in and a capital out. Those are pound defined to nothing. So they make no difference in the code. But in any Vulkan function, you're oftentimes passing things ampersand. You're passing an address. Sometimes that's input information. Sometimes it's what you're expecting back out. These are in the sample code to let you know that. Anytime you see in ampersand something, that means you're passing information into that function. Anytime you see out ampersand something, you're getting information back out. Okay, so that's there for hopefully helping. All right, Vulkan needs to allocate memory for the buffer. It then needs to bind the memory to the driver. This is very much like OpenGL, where you allocate things and you bind things. When you've got your buffer, you create the buffer like on the previous page, Vulkan wants to tell you what its memory requirements are. Okay, and what I've seen so far is the memory requirements that come back are exactly the number of bytes you would have guessed at yourself. So I suspect there's some future enhancement going on here, but you need to do it. So we pass in the buffer, we get back out a structure that gives us the memory requirements. We now need to look for special memory. And Vulkan breaks up your memory into really two pieces. Some of the memory is visible to the host. Well, that's memory you're going to write from your application over to the graphics card. And there is code to do that. This is one of the few places where the sample has a little helper function. Find memory that is host visible. It simply looks at some flags and says, oh, this bank is visible to the host. I will use that for this. There's another kind that says visible only within the device. And by and large, that's very fast memory. That's where you end up putting your textures. Okay? We allocate memory, we bind the buffer memory, and then this part should look pretty familiar for OpenGL fans. You simply do a memory map. That's how Vulkan wants you to get your bytes over to the graphics card. However, you do some setup things first in order to make things prepared for that to happen. Here's the other kind of memory, device local. All right, on the system I was using, this is how the banks of memory were set up. There were two that were device local. There were two that were host visible. You query that. Okay, it's not going to be this way on every graphics card, but it's something that you query. Something I've found useful is there's three pieces of information every buffer needs to have. Its size, where it is in device memory, and the buffer you allocated. You can keep those around separately. I found it useful just to lump them together. Again, I tried as much as I could not to put special things in there, but sorry, this seemed to be a better way to do it. So you'll see that in the code. All right, initializing a data buffer. We do the create buffer like we did before. Here's what we've got. So in C, this is what we're going to try and store in the buffer. Now this is the kind of thing you would pass into a shader. And this is the shader code. So there's a layout, and notice the layout structure looks almost identical to the C structure. And it's meant to be that way on purpose, because what we're going to do is we're going to put this in a buffer, and then we're going to assign that buffer to this data structure in the shader. Okay? And so it very logically makes sense. Down here, since these were matrices, we're calling these mat4s. Up here, we're calling them mat4s. There's a GLM, which is used commonly throughout the graphics community. It stands for GL Math. It's a math library for OpenGL, but it turns out it works really well for Vulkan. So you'll see a lot of examples here. What it's going to do for all of you is it's going to buffer you from having to do the OpenGL deprecated functions yourself. So if you want a rotation matrix, GLM will give you a rotation matrix. Okay? And so here, he's just using the mat4 out of the GLM. So if we were, and again, we're not drawing anything yet, we're just talking about buffers. So if in the matrix structure, we wanted to set the model matrix, we would dot model matrix, and here's using GLM, well, the constructor is the identity matrix. If we're setting up a view matrix, here's the equivalent of OpenGL's lookat. So again, this looks very OpenGL-ish, which is great. And you have to do this, though, because OpenGL does not give you any built-in functions to set up your matrices. All right, so parade of data, it starts in C, it ends up over in the shaders, or ends up in the GPU somewhere. All right, and well, filling the buffer, yeah, okay, we talked about the matrix, or the memory mapping. All right, this is the details of all the code, so all the pieces we saw before all fit in here, and this ends up with binding the memory buffer you created. All right, so this gets us to where I really wanted to be to start, and that is vertex buffers. So if we're going to draw something, we've got a bunch of vertices. We've got X, Y, Z. That's what we need for 3D graphics. Chances are we've got other stuff. We've got colors, we've got textures, we've got normals, things like that. Those are just data. Those are just bytes. And we're going to put them in a buffer, but we're going to call it a vertex buffer because to us it's something very special. It's something that's got extra meaning. However, it is just a bunch of bytes as far as Vulkan's concerned. All right, this is good news for everybody. The topologies that we came to know and love in OpenGL largely are still there. Okay, we've got points, we've got lines, we've got the line strip, we've got the triangle list, triangle strip, which of course is really important for efficiency, and triangle fan. Now, what's missing? What's missing are quads, quad strips, and the generalized GL polygon. Okay? Well, quads were always a weird thing anyway, because polygons are required to be planar, and if you've got a quad, that could be non-planar. So OpenGL gave you a way to mess up the pipeline. And so that's gone. Quads are gone. And the generalized polygon was one of the most inefficient ways you could have to do geometry, and so that's gone too. But the ones you really care about for drawing lines, for drawing triangles, are all still there. And that's great news for people with OpenGL experience. All right, a little bit ago I said that Vulkan uses Y facing down. I've never heard the story of why that is, but it is. Where this comes up and where you care about it is quite often in OpenGL programming, we tend to follow a convention of counterclockwise outer normal. This. If you do that now, then your polygons will really be clockwise. And if you've played some culling games where you say, oh, I'm doing counterclockwise outer normal, cull the clockwise ones, you're going to cull the ones you want. So what I recommend is you just never cull at all, at least until you've gotten your application running, and then you decide whether you want it to call clockwise or counterclockwise. And the way you really do it is you pick one. If it doesn't work, pick the other. Now, how do you handle, oh, come on, you do that. You do that all the time. Don't give me this little chuckle bit. Yeah. Oh, gosh, he's pretty stupid. He does it one way and it sees if it works. Yeah. Okay. Now, how do you handle the fact that y points down? Okay. If you're using GLM, and all these examples are, GLM, because it's OpenGL based, does not do that. If you construct a perspective matrix in GLM, it's going to make y point up exactly like you're used to. All you do is you go into the projection matrix structure within what GLM's producing, and you go to the 1, 1 element and invert it. Boom, done. And so you'll see that in one place in the code, and that's what it's there for. At some point, I imagine GLM will have an if-def, I'm using Vulkan, and then you don't have to worry about it. All right, so this is the kind of thing we see in OpenGL notes. We have a cube. The cube's going to be in triangles. Here are the colors at each vertex. Here are the vertex coordinates, and here are which vertex numbers get connected to form triangles. All right, so in the sample code, if you go to that zip file or you look on the website, all the vertices for the cube, it's a cube, are in a separate file just so it didn't clutter the source code, and called sample vertex data.cpp. And there's a vertex structure, and it's got positions, normals, colors, and texture coordinates like we would do in 90% of our applications. You can leave them out if you want. If I want to leave them out, or if I don't want to use those things, I tend to just leave it in the data structure and just simply ignore the data value in the shader, just so that if I change my mind and want to use it, it's there. And then you'll see data defined. And so this is for vertex 0, and it's got points, normals, colors, and texture coordinates. It's just like you've come to expect. And again, part of the purpose of this section in the notes is to reassure everyone that your drawing doesn't change, or changes only a little bit. All right, here's the part about the culling. Filling the vertex buffer. It's a buffer. All the code we used in the last section works exactly the same. We just treat those coordinates, colors, and so on as a cluster of bytes and write them across. Okay, so yeah, this is really, I should have put this somewhere else. This is the Vulkan pipeline, and a lot of this looks very much like the OpenGL pipeline, and this is the information that we're going to pass in. And so up here, we're going to pass in the vertex input. And so all of these other stages have other ways of getting the information in, but for right now, all we're going to do is we're going to put together these vertex buffers. We looked at this before. If our structure of each vertex looks like this, which is pretty typical in a C program, then our structure of where we're going to hold these things looks like this in our shader code. Now, the shader code is going to be a little bit different because these values are really vertex attributes. And if you've used the non-deprecated part of OpenGL, that looks and sounds familiar. It should look and sound familiar because in the non-deprecated part of OpenGL, vertices, colors, normals, texture coordinates are all attributes that get defined that way as attributes. For instance, in non-deprecated OpenGL, you say GL vertex, and that's not an attribute, it's vertex coordinates. But later on, OpenGL decided, we really need to talk about everything as an attribute to generalize it, and so Vulkan picked up on that. So over on the shader side, these are the things that are going to be defined per vertex. And that's really what attributes are. The attributes are per vertex pieces of information. Okay? And so, well, yeah, of course, position is per vertex. It is the vertex. The normal, the color, texture, coordinates are all per vertex. And so over here on the shader side, we're going to bind those into specific locations. Okay? So this part looks very much like OpenGL. But over here on the Vulkan side, here's probably the first place where we're going to take some of the burden off the driver, or we're going to assume some of the things that we used to let OpenGL do automatically. And that is, we're going to create a data structure that has all this binding information in it. And that's up to you. So that's up to you to say, I want the vertex coordinates to be bound into location 0. That's where the shader is going to look for them, and that's where we want this structure prepared to write them. And so, since we have 4 pieces of information here, we're going to have 4 structs to give some information on. Okay, and so this is pretty typical Vulkan. I'm going to have, in this first element, I would like to give it location 0. I would like to call it a vec3 because, well, it is a vec3. And here's where you find it in the C structure. And you notice it's using the C construct offset of. That's very much like size of. It's something that the compiler looks at and fills in the right number. Well, in this case, its offset's going to be 0 because it's the first thing in the struct. It is really super important in any place you can do it in your Vulkan code to use size of and offset of. If you hard code those numbers, you are going to be editing forever next time you make a small change. Okay, always use size of and offset of every chance you get. And so this is no different. All right, so for the second thing, which is the normal, I want that to be location 1. I want it to be a vec3. And, well, we're 12 bytes into the structure, so this will end up being computed as 12. But again, we don't have to worry about that. So in this data structure called a vertex input attribute description, we've got 4 elements because we've got 4 things coming across as vertex attributes. This capital V, capital K, or lowercase k, is a type def. Okay? Capital V, capital K is a define. Lowercase v, lowercase k is a function. Capital V, lowercase k is a type def. And almost always these type defs are structs. Internal built-in structs. All right, telling the pipeline about its input. We're going to come back and talk about the pipeline in more detail, but the pipeline, what Vulkan calls a pipeline, is a whole ton of information. It's got information on, well, these attribute descriptions. What is it you're going to pass into me when you get around to passing it? It's got information on the shaders. What shaders am I supposed to use? It's got information on the topology. Is this a triangle strip, or is this a triangle fan, or is this a bunch of lines? So all of that lives in this thing Vulkan calls a pipeline. It's almost unfortunate they picked that term because the word pipeline means something sort of more general and has for years in computer graphics. If I had to change it, and nobody asked me, I would have called it the state or the context. And OpenGL uses those terms too to talk about, well, here's everything you need to know. In OpenGL, the state has colors, the texture information, current normal, things like that. In Vulkan, it's got that plus a whole bunch more. And almost always, there's some exceptions, almost always the state is immutable. It's not changeable. So you create a state with all these permutations of things, and that's it. And so really, the way you end up using the pipeline, the state in Vulkan, is you create lots and lots of them. Okay, every combination of shaders and topology and what your input looks like and so on. And some of the game people have told me that in their engines, they end up creating a couple thousand separate pipelines. But the reason you do this is because the creation of the pipelines, all that information is done ahead of time. It's not done while you're interacting with your geometry. When you're interacting with your geometry, you're just switching in various permutations of all the information. Okay? So again, this is one of the good news, bad news jokes in Vulkan, is it's based on performance. And performance says you do not change the state at runtime. You change the state, you create different states at sort of the beginning of execution time. And so that's what it's going to do. All right, telling the pipeline about the input. We're going to come back to the pipeline, but pipeline create info is a big struct. And here are all the things you set into the struct. And again, when we come back to the pipeline, you can see all these ampersands. This is all the structures of information that are going into the pipeline structure. You actually get used to this after a while. Is you say, oh, I need this and this, and oh, I can reuse this piece of information in that pipeline, so I don't really need to recreate it. I can just use it a second time. And then there's this VK create graphics pipeline that takes all those things in. So this is a good example of that diagram that showed all the boxes and arrows going down and down and down. The pipeline is probably the best example of that. All right, later on we're going to talk about something called a command buffer, but I want to just introduce the term now. VK command draw. And there's some arguments in here. This is where you actually tell it, I've got a vertex buffer with information in it. I've got a pipeline that tells you the parameters that I want you to use. Ready, go. And this is the ready, go. You bind the vertex buffer, you bind which pipeline you want to use, and then you say ready, go. So at runtime, at interaction time, the amount of information that you're using here really is pretty small. That's because you created a ton of information up front, and that's where a lot of the performance comes from. All right, so kind of working our way back up. Again, I wanted to start with, let's just reassure everybody that drawing makes sense, even in Vulkan. Okay, so let's talk about the drawing. So we've talked about vertex buffers. So if I had that cube with a certain distribution of colors and a certain distribution of surface normals and textures and so on, I know how to create this. It's just an array of structures. There's two ways of drawing, and this matches OpenGL as well. One is indexed, and one is not indexed. Not indexed means we just grab whichever structure we need for whichever vertex we're trying to draw to next, and we list it. Which means that, say, for vertex number 5, we're going to have anywhere from 3 to 6 times that we list the information for vertex number 5. Now, it appears in this triangle, and this triangle, and this triangle, and this one, and this one, okay? That's not indexed. It's probably faster for that to execute because whatever it needs, it's got it right there, but it's also a waste of buffer space. There's probably times you care and probably times you don't. Okay, so in the first triangle in that cube, it's connecting vertices 0, 2, and 3. And so that means I'm going to list the struct for vertex 0, the struct for vertex 2, and the struct for vertex 3, and I'm going to send them in. I'm going to send them over as inputs to the shaders. The next one is the next triangle is vertices 0, 3, and 1. I'm going to list those and send those into the shaders. And notice I'm listing vertex 0 a second time. That's what you do. Okay? So when you go to do that, you basically are setting up a vertex buffer, which is really a data buffer. And you're just listing all the vertices in the order that they appear in the triangles in what you're drawing. And in the vertex input binding description, you basically are referencing this structure to define what the elements mean in what you're trying to draw. And when you're actually doing the drawing, here's where you finally tell it what vertex buffer to use. Now, when you're drawing, say I'm drawing multiple cubes, and there's other ways of doing it, but let's say I'm drawing multiple cubes, and I've got different lists of the vertices. Maybe I want the cubes to look weird shaped, but still six-sided, okay? I don't need to rebind a pipeline because all the pipeline information is exactly the same. I would just need to rebind a list of vertices. And so that's what's going on here. When it's actually going to execute graphics commands, and you can tell it's executing graphics commands because, well, it's telling you CMD. If I was just using the same pipeline but binding a different vertex set of vertices, I would bind a different set of vertices. And when I want to draw, I would draw. And here's where you can do things that are specific. So here I'm saying within that list of vertices, here's how many I've got. And I'm saying within that list of vertices, here's the vertex number I'm starting with. Now this is actually pretty common in Vulkan. Most of the time you'll see this argument referred to as an offset. And the reason it's referred to as an offset is, where am I starting in the list? Now this is pretty cool actually, because if I'm allowed to give the offset and a count, I can use the same huge list of vertices, and in this particular draw, maybe I'm only using this much of it. And maybe in the next thing I draw, I'm going to use this piece. And maybe I'm going to use this piece. Vulkan does this so that you don't necessarily have to create a separate vertex buffer for every little thing you want to draw. You can pack them in one big vertex buffer and then choose to draw certain pieces at a time. Okay? And that's why a lot of functions have an offset in them. So you can do that, and they have a count in them. Here, again, use size of if you can do it. Here it's just counting the number of vertices by checking the byte size of the vertex array. Okay. All right, so this is non-indexed. There's another one called indexed. And indexed is if indexed allows you to only list the vertices once. So in the case of the cube, I would only list 8 vertex structures. But then I'm going to give integers into which ones to draw next. And so they cluster like this. And so index 0, 2, 3 is going to refer to this, in this vertex array, vertex structure 0, vertex structure 2, vertex structure 3, connect those into a triangle, and we've got it. Again, this is very OpenGL and works the same way in Vulkan. When you go to draw these, you use the VK command bind vertex buffers, because it's a vertex buffer that's holding those structures. You need that. But then you also bind an index buffer. You bind this. And again, what are you binding? Well, you're binding a bunch of bytes. It just happens that you've set up the bytes correctly to be integer indices into what you want for what you draw. Okay. That in that index buffer, you actually can, there's two types, and you tell it which type. One is a 16-bit integer, and the other is 32-bit integer. You can save, if you've only need 16 bits for each integer, you can save a lot of space by doing uint16. If you've got hundreds of thousands of vertices in there, you're going to have to use a uint32, but you get that option, okay? And so then when you go to draw it, it's command draw indexed. And so now it knows to look at both the vertex buffer that's currently bound and the index buffer that's currently bound, and it's got offsets in here, just like before, and it draws what you're pointing to. You know, what happens if the numbers in the buffer are wrong? Well, you get what you get, which is entertaining but not useful. Okay, so that's drawing with an index buffer. There's one other little trick to drawing with the index buffer. Oh, one thing I ought to point out with drawing with the index buffers is if you've got multiple attributes at the same vertex, like for instance, that vertex has yellow no matter which triangle you're asking about. Okay, so if I list this triangle, that point has yellow. If I list this triangle, that point has yellow, and so on. And that works perfectly if you want continuous color. Okay? If I wanted this face to be all yellow and this face to be all blue, then I would have to do something different. I could not say that that one vertex has the same color because it doesn't. So where you find that coming up is something like this. Because oftentimes in objects like this, and what's special about this one is it's got a normal discontinuity right here. If you've got something like a sphere, well, every vertex has the same attributes: normals, colors, texture coordinates. But here in this example, it's got the same colors at each point, but when you go to define texture coordinates, it probably doesn't. And so oftentimes when you do this, you get funny artifacts like this, where the texture coordinate for the vertex right here worked great for this face. Same texture coordinate works for this face. It doesn't work correctly for that one. All I'm saying is be careful how you set up your vertex data. Be careful especially if you want vertices to share multiple attributes. Tell you what, let's stop now. Are there any questions? And if you got questions, I think, yeah, there's microphones up here in the front. All right. Whoop, is that a question? I can't hear from up here, but there's microphones up here in the front. Or we're within half an hour of a break, and I'll just hang out up here during the break. Tell you what, let's do that. All right, so at this point, we've talked about defining geometry using all the shader structures, getting the shader, or getting the attribute structures over to the shader. Now let's talk about the shader on the other side. And what's really going to be important here is the fact that we're compiling it. All right, so this is kind of a shader view of the graphics pipeline. You've got a vertex shader, possibly tessellation control, possibly tessellation evaluation, possibly a geometry shader, the rasterizer, and the fragment shader. This works the same in Vulkan. It's the same pipeline, although more things are exposed. This is how Vulkan lists the shader stages. And there's certain moments in Vulkan programming where you need to tell it that a certain thing belongs with a certain shader stage. Okay? And so there are other things. So here, 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 and here are the ones we looked at. But there's certain things you want to happen at the top of the pipeline. And so they've established a separate define for top of the pipeline, really before where the vertex shaders come in. There's a place where the vertices come in. There's a place where the indirect bits, the indirect integers come in, and so on. And so these are all the things that Vulkan thinks you have access to. Okay? Now, differences from OpenGL. We talked about this before. There's that pound define Vulkan in the shaders, which you can use. You'd say pound if def Vulkan, and then you could put Vulkan specific code after that. Some other things that changed: vertex and index indices in OpenGL. Those are called vertex ID and instance ID. This is a better use of the terminology. Instance, index, vertex, index. It's a way for the shader to know what index number or vertex number is coming through right now, and it can change things. And we'll see an example of that when we talk about indexing. In OpenGL, frag color can be broadcast to all color attachments, not in Vulkan. It broadcasts it just to location 0. I'd say don't use it. If you love GL frag color, do it for your OpenGL shaders. Take advantage of that pound-defined Vulkan, but I'd say don't use it because it behaves differently in OpenGL than it does in Vulkan. Other differences. In Vulkan, you can actually separate the shader data from the samplers. In OpenGL and in Vulkan, you can put the shader data and the sampler in one object that gets passed in. In OpenGL or in Vulkan, you can actually separate them. You can have a sampler and a texture. The sampler defines how you're going to sample the texture, and you can combine them into one opaque data structure. This is handy if you've got one texture, but you want to sample it different ways. Okay, you don't have to create that combined opaque data structure. You can have it as one set of texture data and then multiple sets of ways to sample it. In Vulkan, there's something called descriptor sets, which are used to define how uniform variables get passed into the shader. We'll come back to that. Push constants are kind of a way of getting around the immutability of certain things in Vulkan. And they're actually very handy. And we'll show you an example of that coming up. Specialization constants. Really here I'm just listing what are some of the changes, but I'll define what these things are later. And one of the differences is if you've got uniform variables in Vulkan, you have to use a layout structure. In OpenGL, GLSL, you could say uniform float X, and that would be fine. Here, you've got to, well, this ends up looking like a C structure, and so here is a set of uniforms that define a collection of matrices. All uniforms except for texture samplers have to be done this way. And so it's in your best interest to combine these things into clusters, like here, combining these into multiple matrices, combining this maybe into different light source properties or different lighting properties. Except for samplers. Samplers can be done on a line by themselves. So again, this is a wonderful place for that pound-defined Vulkan, is if you're using a shader for Vulkan, you pound define, or if def Vulkan do this, pound else do it the OpenGL way. Okay, and now you can use the other 90%. We saw this diagram before in the intro. Here's the idea. You get an external GLSL compiler that's part of the SDK. You compile your GLSL code. It produces this intermediate format called SPIR-V. When you run your Vulkan code, the rest of the compiler is in the driver, and you get vendor-specific code that now is your shader you're going to run. Each pipeline you define, each one of these pipeline states has its own set of shaders. Now, of course, you can use them in multiple pipelines, but shaders are given to each pipeline. So when you bind a pipeline, you're getting that pipeline's combination of shaders. All right, how do you compile? The name of the compiler that comes with the SDK is called GLSL Lang Validator. Well, why not GLSL-C? And you give it the shader file. If you're compiling for Vulkan, you say -cap-v. If you're compiling for OpenGL, you say -G. Now, wait, compiling for OpenGL? That's a change they made a year ago in the OpenGL spec. You can do this external compiler for OpenGL if you want to. Again, and there's all these advantages of doing that. But if you're doing it for OpenGL, you have to say -G, for Vulkan -V. That's how it knows about the specifics of what it needs to do. -I, like in C, is give me a directory where I'm going to find .h files. -S is what stage of the pipeline you're compiling the shader for. Is it a vertex shader, a fragment shader? If you use the standard, and these are the Vulkan standard, file name extensions, you don't need this. So if it's a .vert file, then it knows it's a vertex shader. It needs that so that it can make proper judgments. Like, for instance, if you did use GL frag color in a vertex shader, it would know to flag that as illegal. So you're helping the compiler. -O, the name of the binary file, .spv. SPV is SPIR-V. Okay? So here are the standard file name extensions. Here's the V, G, and so on. In Windows, in the SDK, this is just the name of the compiler, .exe. In Linux, it's out there, and in Linux, you got to set the library path, and the name of it is just GLSL Lang Validator. All right, how do you do this? Well, on Windows, you can install Bash. And this is how I've found I really like to run it, because I like to do make files. And it's just convenient for me to say make shaders, and it runs. And so if you're on Windows and you like that kind of thing, install the Bash shell. That just gets rid of a lot of this. If you're running it and you say you don't have the bash shell, then you use the command line prompt, and you just say GLSL lang validator, type in the rest of it, it all comes back. If it comes back with no messages, that tells you it was a successful compile, very much like C. If it comes back with messages, it tells you it wasn't a successful compile. So that's how you know. And so here, he's got a file called sample-vert.vert, and that will end up producing sample-vert.spv. And sample-frag.frag and sample-frag.spv. And so if it compiles correctly, this is how it looks. If you've compiled it on Linux and it compiles correctly, this is how it looks. Okay? And so it's this SPV file that you're going to give to one of the Vulkan pipeline instances. All right, if you care, the SPV files have a magic number. And personally, I like the reassurance, especially if you're using make files, because sometimes an error message pops up and you don't notice it because you didn't type in the line yourself. And so this is code, and it's out of the sample code, but basically what it's doing is reading in the first handful of bytes of the SPV file and comparing it against that magic number. And so it'll shut Vulkan down right away if that magic number isn't what it's supposed to be, because that's the flag that it didn't compile correctly. I just like the reassurance. And now reading a SPIR-V file, this looks exactly like reading a GLSL file into your OpenGL program. You're basically asking it how big is the file, you're allocating an array, you're sucking the SPV file into that whole array, and then you're giving that to the pipeline structure via this shader module create information. So here it's passing in the SPIR-V code, here you're telling it how many bytes it is. Okay? And then that later gets passed into the pipeline. All right, let's talk about the sample code. Okay, so the sample code is included in the notes. It's also out on that website. And it does this. And let me, whoops, I'm sorry.
Do you still need to link the compiled fragment and Vertex shader?
What do you mean the link?
After you compile them, you usually have to link.
Oh, after you, yeah, good question. After you do this, because this is just setting a struct, and pass it into the pipeline structure, after that you no longer need the link. Here you still need the link because all you've done is set a pointer into a structure. But the pipeline is what sucks it in and compiles. And really, the moment you create the pipeline, that's when it does the compile. So at that point, you can reuse, or you can even destroy this array. Was that the question? Yeah, good question. You're allocating so many data structures in Vulkan, it is nice to get rid of them as you go. All right, I've said this before, I will say it again. In the sample code, everything is written out in appalling longhand. It's really meant to be, if you see something and you say, now where did that come from? It came from not very far above it. If you were really doing this, you would probably define a whole bunch of these structures ahead of time, up at the very top of the program, and then when you needed them 1,000 lines farther on, you'd use them. The sample code doesn't do that. You shouldn't have to hunt very much for stuff. Also, it does things multiple times. If it needs a data structure in this part of the code, it creates it. If it needs that same data structure in this part of the code, it creates it. Again, you don't have to look very far up to find how things are being done. Everything is in one big CPP file except for the Vertex structures. You probably wouldn't do that in real life, but again, I wanted things to be easy to find. Yeah, it's not really hiding complexity. Sets up Vulkan structs every time it needs them. At times, the code sets up things that are not needed just to let you know what could have gone there. Some of these structs take in lots of information. If that information's not needed, what you pass in for that value is a null pointer, or you pass in a 0 count. You could leave those out. If it doesn't need something, it's just simply not going to use it. It's not going to look and see if there's a null pointer. But everywhere in there, the null pointers have been passed in, the 0 counts have been passed in, just to show you that, well, if you wanted to put something there, here's the name of it. Yeah, that's probably the things you need to know. And again, I understand this is not what you would normally do. Tough. All right, so here's the sample code. This is really meant to be dirt simple. It's a cube. Well, run, damn it. Can I do this? Nope. Oh, let me do this. I think I might have to turn the pointer off. All right, turn the pen off. All right, dirt's simple. It's a cube. It rotates. It starts out just being yellow. You hit a key. It becomes texture mapped. That's my son's new puppy. All together now. Aww. You can also take it out of rotate mode and rotate it and scale it yourself. You can turn on instances. It's one instance. There's 4 instances. We'll talk about instances. There's 9 instances. There's lighting. Turn on some lighting. Go back to the color mode. Yeah. So that's it. Let me go back to the pen. So that's what the program does. I'm not going to go through this a line at a time. You've got the notes, you've got the sample code, but I do want to every so often point out something really good. Probably not here. There's a function in there called initialize graphics. That's got everything in it. And what it's done is it's broken it out into, let's initialize the Vulkan instance. Let's create the debugging callbacks. Let's initialize the physical device and so on. And the way it works in the sample code, these are, well, there's a number built into each function that basically tells you what order things come in. And they don't have to come in that order. It works. Sometimes you can mix up the order, sometimes you can't. But that's what you'll find. And so the init graphics calls separate functions to initialize everything, and they're in a certain order, a certain number order, and there's certain names like initialize the render passes. Okay, so that's all set up for you. The Vertex data is in this separate file just to keep it out of the code. The Vulkan software philosophy, we ought to spend a moment on that. Vulkan was written for C. You can use it with C++, but by and large, it's going to look like you're doing C, except for your own data structures. So for instance, if we were doing C++ object-oriented programming, we would probably have a function or a method called getDeviceQ. And because that's owned by a logical device, we would say logical device points to that. In Vulkan, instead of that, things like logical device goes into the first argument. So if we were doing in C++, we would do this. Vulkan does it this way. Okay? But it's the same thing. It means that that particular logical device owns what happens in here. And you could have more than one logical device. All right, conventions we've talked about. First two letters mean everything. This is a recurring theme in Vulkan. Actually, other standards too. If you do OpenGL, this is a recurring theme in OpenGL. Sometimes you need to create data structures, but you don't know how many of them to create. You want to create an array of structures, but do I need 1? Do I need 10? And so the first thing you do is ask it, how many am I going to need? And so here it is saying you need count. And count is an ampersand, it's coming back out. Notice the name of the function, enumerate physical devices. And down here, there's enumerate physical devices. Well, this last argument is a null pointer, which means only give me the count, don't actually set any data, because I'm not ready yet. This part in here, and here's where you can use C++, is it looks at the count and it creates the correct number of structs. Now it calls that function again, and now the last argument does have something in it. Okay? So this is a recurring theme. You can play games with the vector standard template library function that's in C++ if you want, but this is probably the easiest way to do it. And that's all you've got to do is get the count, set up the number of structs, pass it in, you're good. Now you know that it's not going to overflow an array, so that's a big help. All right, the sample code, yeah, there's a bunch of stuff in it. It's everything you need. Okay, if you're on Windows, you should be able to double-click the SLN file, bring up Visual Studio, off you go. All right, so two more things that I'm not going to cover, but I want you to know they're there, is GLFW is a windowing package. It's meant to be used in a lot of different things. It can open a window on a Windows system. It can open a window on a Linux system. The sample code uses it. It's really nice. It's got built-in links into Vulkan. So when you're looking for, well, I probably didn't put it in. You'll see it in the sample code. When GLFW and Vulkan need to know about each other, GLFW has a function to do that. It's got the word Vulkan in it. So when a GLFW creates your window, it's got an internal pointer to that window. Vulkan needs to know that. It needs to know where you're going to be drawing into, and so it passes it in, or passes it between them. That's great. The thing I like about GLFW is it looks a lot like GLUT in the OpenGL world, and beyond that, I don't really have to know very much. I'd rather spend my time writing the Vulkan code. When I said it looks a lot like GLUT, it has a keyboard callback, it has a mouse motion callback, it has a mouse button callback. All that looks the same as in GLUT. If you want to check on keys, well, here's what you do. If it's the M key, do this, and so on. And then inside the main program, it does a loop. It's not event-based, it's loop-based, although I suspect there's some event handling in here. Here you're just asking it, you're polling for keyboard, mouse, and so on, and then you update the scene, then you render the scene. And it just does this looping forever and ever. So there are other ways of doing this, apparently. I've heard other people talk about things. This is one I know works, and it's in the sample code. The other thing I'm not going to go over an item at a time is GLM. This is the GL math. And if you just Google GLM, you'll find it. It's included in the zip file. It was really written to allow you to do nice OpenGL math things. Put together a rotation matrix for all the things that are deprecated. Okay? It's got some of the same type defs that the shaders use. So it's really nice. Here's where you can find it if you want to go look. I'd recommend just Googling it because that version number changes all the time. Yeah, and so if I wanted to create a matrix that had the look at information in it, like OpenGL does, I would use the GLM ; look at, pass in I looking up, and I would get back a matrix. Okay, which in this case you would pass over to Vulkan as a uniform variable. Okay, so GLM does a lot of different structures. MAT4, VEC4, VEC3 are the most useful. Those are the ones you're going to use to fill OpenGL variables in the shaders. Different operations, they replace what you're used to in OpenGL, which I like. Ortho, frustum, perspective, look at, rotate, translate, scale, if that's what you're doing. And it's all there in the sample code. So you can get at it from the GLM, or you can get at it from the sample code. All right, so there are a whole bunch of things left, and an hour and 15 minutes or hour and 30 minutes left to do them. I'm going to make sure we get to the most important stuff. If I think we're running behind, there are things I might lightly skip over. All right, but instancing, I think, is pretty important. In the sample code, in the little video, you saw 1 cube suddenly becoming 4 cubes, suddenly becoming 9 cubes. There are a lot of graphic scenes where you want to draw the same object many times. Okay, and when I say the same object, I mean, well, the same number of vertices and almost the same coordinates. Maybe you're going to change the coordinates a little, like moving the cube to the side. Maybe you're going to change the colors. Maybe you're going to change the textures. But it's pretty much the same object. And this comes up a lot. You know, spheres in a molecular modeling program, for instance. And this is where instancing comes in handy. And you've seen this before in the command draw. What we saw is something called instance count and first instance. So if I want to draw the same cube 4 times, I set the instance count to 4. Now, what does that do? And that's where we're going to get to next. So in the Vertex shader is really where the instancing takes place. Yes, we're going to give it here, but we're going to implement it there. And so let's say I wanted to do the multiple cubes. What I would do, and to do them side by side, what I would do over here is I would set up some kind of logic that says, well, if I'm the nth instance, how am I going to handle that? How am I going to color it? How am I going to shift it over? What am I going to do? And then we simply look and see what the instance index is. And so, for instance, here are some colors. Actually, let's go back here. So here's the instance index, and it's using that to offset the x's and y's. And so that's how when you hit the 4 key, it becomes a 2x2 mesh. When you hit the 9 key, it becomes 3x3. It's looking at the instance index. And this is in the Vertex shader, and this gets passed in automatically. It's a built-in variable in the Vertex shader. There's another way to use the instance index, is you can actually set up an array of information and pass that in as another uniform variable, and then use the instance index as an index into that. So if you don't have logic, but you have a list of what you want to have happen, you can do that. And so I said, this is really helpful. This is in OpenGL. It's just not a feature that many people have heard of, but it works very well in Vulkan. All right, descriptor sets. Descriptor sets are one of the new things that go into Vulkan. And the setup of them is, well, I find probably more complicated than it needs to be. But it's really important to have them, and here's why. In OpenGL, we did something like this, is we would set up a uniform variable, give it a name, another uniform variable, give it a name. Because Vulkan has now pushed back so much responsibility on the shaders in Vulkan, you are going to pass in a lot of uniform variables. And the problem is this list gets very, very long, and it's really not always necessary. For instance, a lot of times when we're drawing, we want to do sort of a hierarchical drawing like this. So the whole scene may need certain numbers of uniform variables. Okay, let's pass them in. And now for every object in the scene, each object has a separate set of uniform variables it needs. Same uniform variables, but different assignments. Well, if we're doing that like in an OpenGL, we have to pass in everything. And for every draw within the object, we might have another set of uniform variables. And so really, because Vulkan is pushing back so much responsibility on the shaders, you need to do this a lot. Like for every draw within an object, I may swap out uniform variables a bunch of times. I'm changing colors, I'm changing some attribute of the textures, okay? But then for each object, I'm going to swap out some things, but each object is going to have the same values. Well, there's no good way to do this in OpenGL, but there is in Vulkan, and that's this thing called descriptor sets. And descriptor sets really just describe each set of uniform variables, but it lets you cluster them. It lets you group them in groups so that when you're swapping them in and out, swapping different values in and out, you only have to do it when you need to, only have to do it when you want to, okay? So our example is going to assume this, where we've got matrices, some lighting, some miscellaneous stuff, and a texture. So when we're creating this, it's important to realize that we've got all this data is in C structures somewhere, and all this data has to end up over here. But in between, if you could peek at it, it's all just zeros and ones. It's all just bits. It's all just bytes coming across. Okay? And so the descriptor sets, they're part of the pipeline. They end up being created to hold this kind of information. Now, apparently, descriptor sets are relatively slow to fill, to make. And so what Vulkan wants you to do is create a bunch of descriptor sets ahead of time and then fill them later on. And this happens in a couple places in Vulkan. And these are called descriptor pools. And so all these we're simply creating a bunch of empty descriptor sets that we're going to fill later. But we're going to do the slow thing earlier on. Now, here's what I think. I think of a descriptor set or descriptor sets as sort of like the Rosetta Stone, where it's giving you information about how to interpret each set of uniform variables as you've clustered them. And so since we had 4 sets of uniform variables, we're going to create 4 descriptor sets that describe them. And so this is a uniform buffer. There's different kinds of descriptor sets. So uniform buffer is probably the one you would use the most. Here we're creating a uniform buffer, here a uniform buffer, and here an image and sampler combination. Here is where we're going to tell it what we're creating, and we're going to tell it what stages of the pipeline are going to use this. If you're not sure or you don't care, you can just say every stage of the pipeline is going to use this. Vertex shader, fragment shader, geometry shader. There are certain optimizations Vulkan claims it can make. If you're only going to use it in the vertex shader, you tell it you're only going to use it in the vertex shader. So here it's saying, I'm only using this one in the vertex shader, which makes sense. It has matrices in it. This is one I think I could use in both the vertex shader and the fragment shader. You just OR the bits together and you get multiple meanings. So this is the kind of information you're supplying to the descriptor sets. All this information comes down to right here, where you end up with an array of all the descriptor sets you've got, with all the information about how they were created and what they were created for, and then that ends up in the pipeline. When it gets down to here, it looks like this. Okay, here's the layout of that descriptor set, and here's where it is in the C program. Okay, this is where the link happens between your C data and what's going to end up in the Vulkan data. Here's the second one. Here's the third one. Here's the fourth one. Here's the array. And then we're going to create the pipeline layout. Okay? And there's two pieces that go into the pipeline layout. The pipeline layout is really there so that you can the pipeline, when you're creating the pipeline, it knows how big to make certain parts of it. It's going to do some dynamic memory allocation. There's only two things that end up in this category, and one is the descriptor sets, and one is this magic thing called push constants, which we'll come to later. Okay, but this is what it needs. And so it's going to pass those in to another structure, and then the pipeline is going to use that other structure to create itself. All right, so allocating the memory for the descriptor sets, this is what's going in here. Again, we've got 4 descriptor sets. We're going to do 4 memory allocations. Like before, we were telling it where the CPU data is. Here is all 4 of them coming together. And here's the really important part, is this is where you create the pipeline. And we've been talking about creating this pipeline and many of them. The pipeline is essentially a permutation of all these properties. And you can see that here, because you can see that it's passing in the address of a lot of structures of information, including the descriptor sets. Okay? And then, just looking ahead, here's where you bind the descriptor sets. So while you're drawing things, remember this CMD is a Vulkan command which binds things, or which executes things. And here you're taking that pipeline layout and the descriptor sets, and you're making the execution part of, or the command part of Vulkan, you're telling it that this is what the values are to be right now. And so you would have multiple calls like this that would swap out different descriptor sets, different pipeline layouts, render some things, bring in different combinations, render some things, and so on. But now let's talk about a little more detail about what the pipeline is. Well, gosh, this is the pipeline. There's a bigger diagram of this coming up. Don't worry if you can't see this. But this is essentially what OpenGL would call the state or the context. And it all has to do with all the combinations of stages that you need to render the thing you're about to render. And so anything that describes some feature in a stage that's going to affect the appearance of something you're about to render goes in the pipeline. And that's why you end up creating dozens, hundreds, maybe thousands of unique pipelines, and you try and do it at the start of the program so you don't pay for those creations. Sometimes I think you just can't help it, is you need things and the information isn't available till you're interacting. But as much as we can, we try and do that ahead of time. So this we saw before. We saw the pipeline layout, and it had descriptor sets and this thing called push constants. That's to set up some dynamically allocated structures inside the pipeline. Everything else that goes into the pipeline is values. These are the values, the graphics values, that go into the pipeline. So for instance, which shaders to be used, what are the vertex attributes? That is, what data is coming into the pipeline in the vertex shader? The topology, the viewport, the scissoring, rasterization information like culling, depth and stencil. So really anything that affects drawing has to be set in the pipeline. Now you notice some of these are drawn with bold italics. Originally, the pipeline was supposed to be totally immutable. That is, you couldn't go back and reset things. These things that are in bold and italic, you can now. So if you're using a certain pipeline and you decide you want to use the same pipeline but change the line width, you can just change the line width. And this is something we do down in the rendering in a CMD, a command type function. But for the most part, things get set and get set once. All right, so again, I don't expect people to look at this much right now, but you see things like, well, let's see, here's the vertex input attribute, and what goes into that? It goes, the locations, the bindings go into this structure. This structure goes into the vertex input structure. This structure goes into the pipeline create structure, which ends up creating the pipeline. This is how pipeline creation works. This piece of information goes into there, goes into there, goes into there, creates the pipeline. If you were the Vulkan driver, when you got to this, you would probably go the reverse way and start pulling information back out. Okay? But all of these things have to be done. Have to be done before you have a pipeline, which has to be done before you actually do any drawing. Again, it looks just amazing right now. It's actually something you get used to, and there's a lot of things you use multiple times. The sample code recreates everything as soon as it needs it. But what you would really do is you would say, well, if I'm going to use positions and normals and colors and textures, I would create that structure once and then use it multiple times. And so every time you create a pipeline, it doesn't necessarily look like this. It may look like only a handful of things get recreated specifically for that. Okay. All right, there's a function that I found useful in the sample code because what I found is, by and large, I was reusing a lot of those settings. And so there's an init graphics vertex fragment pipeline where you pass in the vertex shader, the fragment shader, the topology, and the rest of the pipeline. Because I was finding over and over that's all I needed specifically. And so this creates a new pipeline with only these pieces of data changing and these pieces of data remaining the same. And I suspect that's what you'll end up doing too, is you'll find a lot of things you reuse over and over, and only 4 things ever change in each of your pipelines. Here's where you link in the shaders. The shaders, if we go back to here, the shaders are right here. And so there's a pipeline shader stage create piece of the pipeline, which goes here, which goes here. When you've got the SPIR-V files, this is all you really need to do, is you need to come into this section and pass in the SPIR-V binary there, and pass in the SPIR-V binary here, and off you go. So really, we're just plugging things into data structures. Here's where you link in attributes. And so the per vertex attributes we looked at before, we're using position, normal, color, and texture coordinates. And so here's where you tell them about that. The first one's a vec3. The second one's a vec3. The third one's a vec3. The fourth one's a vec2. So here we're telling it about what's coming in and how big it is, so that the pipeline can say, well, here's how to separate everything out. Notice the pipeline doesn't know what to do with it. That's up to the shader. But what the pipeline needs to know is how to separate everything out from what's being sent across. Here's where it's setting the topology. Again, I don't want to go through this a line at a time, but I want to point out the important stuff. Here's where you would say, is this a point? Is it a triangle? Is it a triangle strip? And so on. Each pipeline can only have one topology. If you're doing different topologies, they have to create different pipelines. Yeah, if you're using tessellation and geometry shaders, here's where they get assigned. Primitive restart. This is something handy if you're doing indexed rendering, where you're using the integer indices in order to only have to list the vertices once. What happens if you want to start a new primitive, a new triangle strip, but you're at the end of an old one? There's not a carriage return that lets you go around and start a new one. Well, there is a carriage return that lets you start a new primitive, and that's called primitive restart. And if you're doing indexed rendering and it finds this number, if you're doing 16-bit indexed rendering and it finds this number, it knows to restart the primitive. It really is a carriage return. If you're doing 32-bit, then the restart index is this one. Basically, in both cases, it's not 0. Okay? I found that's really handy. I do a lot of topological rendering. And so if you're doing strips that represent parts of a topo map, well, I could do a triangle strip here and a triangle strip there and a triangle strip here, or I could make it all a triangle strip, one big triangle strip, and do the primitive restart. So it would go down to the end of one triangle strip, primitive restart, carriage return down to here, do it again, and that way I can stuff all of my vertex coordinates into one large data structure and do it with one pipeline. Okay, or with one render rather than having to do multiple renders. So this is handy, and this is another feature in the pipeline. Basically, in the pipeline, it's either true or false. Look for the primitive restart or don't look for it. Here's where you create viewport information. How big is the viewport inside the window? Here's where you create here's the rest of the viewport. You can also do scissoring information. Now, oftentimes there's a lot of confusion about what's viewport, what's scissoring. If I start with this original object and I reset the viewport impacts vertex coordinates. So if I reset the viewport to starting up here, it's going to squish my scene. okay? Because now it's saying, take the full window, but only render it into this much of the screen. The aspect ratios are no longer the same. It'll squish my vertices. Scissoring, on the other hand, operates on fragments. And so what scissoring does is, if I say scissor to here, it just eliminates the fragments that are down there. Now, sometimes the effect of viewport and scissoring looks about the same, but they're not. One's a vertex thing, one's a fragment thing. And you can set the rasterizer state inside the pipeline. You have modes of rendering like OpenGL it has. You can fill, you can do edges, you can do points. Even if it's a polygon, you can render it as points, you can render it as lines. You can also do culling, looking for front-facing or back-facing polygons. Here's where I recommend you turn that off until you're used to the Y facing down, and then turn it back on and see if it works. These are variables that can be set dynamically, can be set after the pipeline's been created. And so these are actually some of the most handy ones. It is really handy as you're rendering to change the line width, rather than having 100 different pipelines for 100 different line widths. You can be changing the line width on the fly. In order to do that, though, you have to tell the pipeline which ones are capable of being changed. So the pipeline creation has to be prepared for it. But the good news is you can do it. If you tell the pipeline to be prepared for it and you forget to actually change them when you're doing the commands, you'll get an error because the pipeline's looking to make it happen. Again, front and back faces. This also comes up in the Z buffering. Do I want a Z buffer on things that are facing, or that are deeper or shallower? Stencil operations are kind of neat. You can use them to prevent Z fighting. You can do outlines really nicely. You can do magic lenses. You can do shadows. So the stencil and depth buffering information goes into the pipeline as well. Putting it all together, and again, the important thing of this is to look how many things come into the pipeline. How many structures have to be set. They themselves having structures that had to be set. Comes down into the graphics pipeline. You get back a structure. That's the graphics pipeline. And you're surely going to create more than one. And then when we're drawing, we just tell it which pipeline to use. And here's where you get all this back in performance. All the pain of making those pipelines, you get back right here. Because the moment you say this, it swaps in all those values. And the next render command you execute right here uses all those values. Okay, so very fast. Pipeline render, pipeline render, pipeline render. And of course, that's what Vulkan's all about. Now, we've been talking about commands, functions that begin with VK, CMD. Let's talk about that, because exactly what is that? Well, those are commands that go down into the graphics pipeline. See? So those are pretty important. Now, we talked about command buffers before, and we have command queues. You fill up the command buffer. You fill up the command buffer. And eventually, when you're ready, you say, now, flush this to the queue. The command buffer, the commands you've been saving don't get executed until you flush it to the queue. And this is why multi-threading is so natural, because you can have multiple command buffers and just flush them to the queues when you're ready. And each command buffer can be filled independently of the others. Queue families. Queues get created out of queue families, like descriptor set pools. They apparently are time-consuming to create, relatively speaking, and so you create them ahead of time. You create query family pools, and the query families can create queues for different things. A graphics queue, a compute shader queue, and a transfer queue. Most of the time, of course, we're creating graphics queues. But you have to specify that when you're creating them, and you can find out, you can query what your system is able to do. And so on mine, it was able to create up to 10 or up to 16 graphics queues and up to 8 compute queues. Okay, that's how many queues I need. And then you'll allocate them from the family of queues. Okay, so when we need a queue, we now have a device queue create information, and we get the device queue by doing that. Here we're setting information on what it is we're looking for. Okay, I made this little function so I didn't have to go through the looking process. But basically, it's looking for one of the queues that's able to do graphics. When it finds it, it just uses it down here. So think of it in terms, though, of this diagram. This diagram. We're flushing commands into the queues in order to be executed. All right, creating the command buffers. The command buffers are basically just arrays to stuff the commands in. There's something that will point into the queues. You create those by calling allocate command buffers. And the characteristics of what you want them to be are all right here. So that when you're done, you end up with an array. You end up with an array of command buffers. And now you can start writing into those. And if you have multiple threads, typically you'll write into different command buffers. The sample program is one thread only, so it's writing into one command buffer. All right, so when you're ready to start writing commands, you say begin command buffer, and when you're all done, you say end command buffer. Here you're passing in one of the command buffers you created. Okay, so now you're ready to start writing. In the diagram, this looks like this, is we created all the command buffer information, and then here's where we start. Here are all the commands that you can use to write into a command buffer. Well, it's actually half of the commands you can use to write into the command buffer. And there's a lot here, but for instance, in this first one, here's a bunch of the drawing commands that we've seen before. And they don't start doing what you've asked them to do right away. You're just writing them into a command, which eventually you'll flush to the queue. Here's the other half. And so there's a lot of them. And so a lot of things happen by writing into the command buffer. Here is rendering. And rendering, as we saw before, rendering had some number of these VK commands. So here we're beginning the commands. Now, I think in the next section, we're going to talk about something called swap chains. Swap chains are the Vulkan equivalent of double buffering in OpenGL, where you've got a list of places you can put images. And so up here, before it starts executing commands for the command buffer, it's going to acquire an image. And this thing called swap chains in Vulkan is like double buffering in OpenGL, except essentially it's a ring buffer of an arbitrary number of images. So before you start rendering, what you want to do is acquire one of those images and now start rendering into it. So here we're doing begin the command buffer. Here we'll start generating information that we need. And the first piece of information we're going to supply is begin the render pass. the render pass has a lot of information in it. And so here is creating the rendering information, which uses clear values and depth values and stencil values. Again, it's things pointing into other things, pointing into other things, pointing into other things. But when you're going to create a render pass information and then begin the render pass, and here's where you're giving it the command buffer to put it into. So again, it's like those little block diagrams with the arrows. This goes to this, goes to this, goes to this, and then we use it. These are the kinds of things you would set up ahead of time normally. Here it's being done right before you need to use it. Here it's setting up, here are things it's going to set dynamically, and so it's setting up viewports and stencils. Here it's using the command to set the viewport and the scissors. Here it's using the command to set the scissoring. Here it's binding the descriptor set to use. Here it's binding the push constants to use. Here it's binding what vertex buffer to use. Here it's doing the draw. And of course, you can do multiple draws. Here it's ending the render pass, and here it's ending the command buffer. So that, but expanded by a large number, is what you would do to do some drawing. Submitting it to a queue, we're going to create information on how we want to submit. And a lot of that information has to do with synchronization, which we haven't come to yet. The synchronization is there because, when we go back to the CMDs, Vulkan wants all of these to be able to run flat out. That's the really important part, is if I execute one of these CMDs and then I execute another one, the first one didn't block. The first one didn't stop. The first one didn't tell the second one to wait. The first one starts executing, then the second one starts executing, then the third one starts executing. Okay? They want to run flat out. And if you don't want them to run flat out, and quite often you don't, then you start doing synchronization. You start setting up semaphores. And there's a whole section on synchronizing. But that's what a lot of this is for, where we're going to wait on semaphores or wait on fences that we created. Okay? But the fact they all run flat out is what the important part is. Okay, so that's sort of the command buffer process, and we submit to the queue when we're done filling the command buffer. We can then reuse the command buffer to do some more filling. Other command buffers can be being filled at the same time. All right, let's talk about this thing called the swap chain. In OpenGL, we talk about double buffering. We have two color frame buffers. We're filling one while the user sees the other. Then we swap their uses. There's only one depth buffer. There only needs to be one depth buffer because we only need it the moment we're rendering. Because Vulkan is trying to run flat out, and because there's different command buffers and different queues, it may not know at that any given moment what the state of a back buffer and a front buffer is. In fact, we may be having a buffer that you can see and another buffer that's been rendered into but hasn't been swapped yet, and another buffer we're rendering into now. And so what Vulkan's done is make a more general data structure called a swap chain. And so rather than thinking of it like OpenGL does, it thinks of it more like this, except it's actually a ring buffer, so it would go back around this way. And so really what Vulkan is doing is it's switching between these different frame buffers, looking for one that's been rendered into and is ready for the user to see. And this is known as a swap chain. Okay? Now, as long as it's called a chain, here's how I like to think about it. Is I like to think of the swap chain as a couple of links on a bicycle chain. And the bicycle chain is going around and around. And when the link's down here, it's going to be being drawn into. And when the link gets up here, it's going to be presented. It's going to be shown to the user. Now, the difference between this is there are lots of links. And so this could be being drawn into, and it would move on. And the next one could be drawing into. And then they eventually get around and they get presented. So there's not the fixed synchronization that, say, an OpenGL double buffering system would have. But we can treat it that way. And so when you're setting up the swap chain, back when you look at the physical devices, which we haven't talked about yet, but the physical devices will tell you how many separate images are able to be in the swap chain. Okay? And you can print that out. And on the system I was on, it printed out 8. So it had a maximum image count of 8 that it could look at. I ended up doing 2 just so it would kind of emulate double buffering. But I've been told 3 is better, so that's something I'm going to try later this summer. There are different formats the swap chain can take, different kinds of images, different ways the images can be stored. You get to set that, but there are some that your device is capable of doing. And there are different present modes. You get to pick that, but there are only some your device is capable of doing. So this is the kind of thing device drivers used to do, is query the device and then set some things up. Now that's your job. All right, so the swap chain, well, ends up here, but again, there are multiple structures pointing into structures to make it do that. The important ones are the image count, the format, the color space, and the present mode. These are the ones that really you've got to ask your device, what are you capable of supporting? And then when you find that out, here are the things I want the swap chain to be able to do. You set up some things ahead of time. I always just put it into a for loop with the image count. So if I'm emulating double buffering, that goes around twice. And so it sets up both those images. So that at any given time, I can write into them, and that will have meaning. You can set up mapping. You actually can swizzle the colors. When you write to red, it really could be written into the green channel. Never done that. When you're ready to render, you ask the swap chain, what's the next image that I'm not using? And it returns it back to you. It gives you back an index, which you then start using. Okay, so really it is like the links on a bicycle chain. All right, so here we're rendering into the swap chain. The fence is a kind of synchronization. And so we're creating the fence, and later at the end, we're going to be waiting for the fence. That is, we're waiting till the whole rendering process is finished before we allow this to be presented to the user, very much like double buffering. So this is the kind of thing you set up for yourself. Here we're submitting to the queue. Here we are. Oh, here we're waiting for the fence, and then we're allowing the user to see that element of the swap chain. So again, I think this maps very nicely to what we all know as double buffering, except for you have to do it yourself. Except you have to monitor it yourself, and you have to synchronize it yourself. But what I've found is that this is the kind of thing you write once and probably never have to write again. All right, let's talk about the rendering process. Rendering ends up here where we create a frame buffer, but we have all these steps in between. Rendering does a lot of stuff with the command buffer and the queues. So in the sample code, you'll see a function called render scene. And render scene is where the VK commands are to bind the pipeline, bind the descriptor sets, bind the vertex buffer, draw the vertex buffer, and so on. There's some other things to be aware of, and that has to do with some of the synchronizing. Actually, let me hold on to that we get to the synchronized chapter. I think that'll work better. But it ends up in the whole rendering process. Yeah, okay, we'll come back to the synchronization. All right, let's talk about textures. Textures are a really interesting process in Vulkan. You don't simply load them and bind them like in OpenGL. You do what probably OpenGL is doing underneath in the driver. And here's how it works, and I'm not going to go through the code a step at a time. You've got the texture coordinates that you've already created here in the data structure for Vertex attributes. You're going to load those the way we already looked at into the Vertex buffer. But now we have to figure out how to load texture images that go with that. And we've got a structure that's going to use a sampler. We just have to somehow get the sampler, the data, the texture data over. Well, there's multiple memory types in Vulkan, and one of them is host visible, and one of them is device local. And these are both GPU memory, okay? But it's divided up into this one. This one is meant to be probably slower, but it's meant to be something you can memory map from the host. And when we looked at buffers, that's how we got the buffer across. We did a memory map from the host, and we wrote it over here, okay? And we used it from over there. But texturing is meant to be a very fast, efficient operation. It has to be. Look at what you're doing. Look at what you're doing with grabbing all those texels and sampling them and averaging them and bringing them back out and stuffing them into pixels. And so this memory is meant to be much faster. And this memory works within the GPU and is not touchable by the host. So this is where we want the textures. This is where we've got the textures. How do we get them over there? We can't get them over there directly. So it's a two-step process. We're going to copy the texture information, the red, green, blue A, to here. Then we're going to copy it to there. Okay, and so it's going to end up exactly where we want it, exactly where the shader wants to find it. It's just going to be done in a different way. All right, so you understand all of this. I'm looking at the time. Okay, so here's where we're going to do that multiple step process. So this is out of the sample code. This is to create a staging image. Staging image is a Vulkan term for put it on the host, or put it on the GPU in host visible memory, knowing that we're going to copy it over to the device memory a little later. Okay? And so they call that a staging buffer. And so this is the information you do. You do an image create info. There's a whole bunch of information about size of the image, format of the image, all the stuff you think images need to know about. There are choices for what you're going to use the image for. Potentially the Vulkan driver can use that to optimize. And then you call VK create image. So the VKs are Vulkan instructions, but they're not CMDs. They don't go into the command buffers. They get executed right now. So we've now created an image with those characteristics. We do all the things we saw earlier about moving things into data buffers, because really from here, It's a data buffer, just like we were talking about this morning. And we copy into it. There are some special functions, bind image memory, get image resource. Because that's an image, there's more things you need to know. But essentially, we've created a data buffer. Then we do the map memory, just like we did before with data buffers. We copy it over, we unmap it, and now we've got it. Okay, so now we've got it, first step. We've got it over in the host. What we need to do next is copy it into that second buffer. And the process looks very much the same. You allocate memory, but now you're allocating memory in a different part of memory. And so here we're using, instead of find memory that is host visible, we're using find memory that is device local. So it's the exact same process. We're doing a copy, except we're copying into a different chunk of memory. Now, clearly something else has to change because we're not going to do a memory map anymore to get it over there. And so there's an operation that actually uses the graphics pipeline in order to do the copy from one memory buffer to another memory buffer. And that's what's being done in here. And so when we set up command buffers, we actually set up two. One for the graphics commands that we knew we were going to do, and one for the transfer commands that we knew were coming now. So you'll see that down in the code. So when we're all done, what we have is a texture memory that's over in the device local memory space that's accessible by the shaders. How is it accessible by the shaders? It's accessible by those descriptor sets. Okay? We tell the descriptor set that defined the shader sampler, we tell that descriptor set about this device local memory. And so now it knows how to link that into what the shader is going to be looking for. This is why I sometimes think of the description shaders as being like the Rosetta Stone. There's just a translation going on there between how things are stored and how the shader wants to see them. Yeah, so here we're setting that up. And then when we're all done, we do something called an image view. And an image view is where we tell Vulkan that this is an image and we tell it what it looks like. And so this is where we link it into how Vulkan wants to see it. So the texture operation really is two steps. Host to staging buffer to device buffer. Okay? Other than that, it looks the same to you because you're accessing it through the shaders. You're accessing it through a sampler, which is exactly what you've been doing in OpenGL. So this is what's different. All right, next let's talk about physical devices. We started down here with how to do drawing. Now we're going to end up here. Oops. Now we're going to end up here in these things called physical devices. When Vulkan drivers get loaded, they know about what hardware they're made to deal with. You could have one graphics card, you could have two graphics cards. Each one of those would be a physical device. You could have a built-in graphics chipset. That could be another physical device. But the important thing is the drivers are who knows about that. There's really no way for you to go out and query what devices you've got without the drivers able to do it for you. Yes, you query what devices you've got, but the drivers have to be set up in order to do that. And here's how you do it. We've actually seen this function before. It's when we were talking about how you sample the count of something, set up arrays, then go get the information. So here we're asking, how many physical devices do you have, Vulkan? And Vulkan's going to reply by going out and looking at the drivers and asking the drivers, and then coming back with the count. Here we're going to set up a physical device array of structures, and here we're going to fill it. So now we have some number of arrays of physical devices. You really want to find out what's in the physical devices. So there's ways of asking it. And the ways of asking it look like this. Since we know how many physical devices we have, we can put a for loop in there, and then there's a get physical device properties Vulkan call, and we pass in the pointer to the ith physical device. That returns us back a struct. And the struct has a whole lot of things in it. And you can just print those out, or you can make calls based on what those values are. I did it, and it looked like this. It printed out the API version, the driver version. I only had one single graphics card. This is the NVIDIA vendor ID. This is the device ID. I guess that's the card number. It flags it as a discrete GPU. It tells me which one it is. And that's device 1. And here are some of the features. There's a lot of features. These are the ones I cared about. Now, what's interesting is if you do this exercise again, I went and did it again on something that had the Intel chipset. Well, here it's got, of course, a different API version, different device. Isn't this cute? Intel's number is 8086. It flags itself as an integrated GPU. It tells us what it is, and it tells us characteristics. Again, this is what you do. Is if you want to make your code run on lots of different devices, you have to be ready for the many different devices. Fortunately, there are ways to query it. And the Vulkan driver has to be loaded on that device or for that device. Otherwise, you won't find it. The devices have different memory. And so you can query that. When I queried that, it said, oh, you've got 2 banks of device local textures, and you've got 2 banks of host visible. OK. So now I know what to go get when I need it for different things. Again, if you want it to run everywhere, you've got to be able to do that. You can ask it about the queue families. Remember, queues come in families that this device sets up ahead of time. You just allocate from the families. Here's what I got. I found I had 16 queues capable of doing graphics. I had 8 queues capable of doing compute, or 9 queues, I guess. And you'll get something different on every device you're on, but it's important to do that. Now, the moment you do this, this is pretty much the last time you deal with physical devices. You know what you've got. You know what it's capable of doing. You're not going to ask it to do something it can't do. Okay? Vulkan then puts a layer over the physical devices called the logical device. And this is not uncommon for a lot of things where you've got some virtual layer over top of it. And the logical devices go here, and the queues belong to the logical devices. Typically, you don't have as many over here as this is showing. You know, typically, you've got more something like this. You create the logical device essentially by asking the physical device for it. And there are some characteristics you can ask for. For instance, you see something here that's asking for layers. What is a layer? One of the cool things in Vulkan is Vulkan allows you to slip some code in. So there are, well, let's try and draw a picture of it. So let's say there are Vulkan commands coming in, and there are Vulkan commands that are going down to the hardware, like you want them to do, you are allowed to slip pieces of code in here that get executed between there and there. And those are known as layers. And the layers are useful for things like debugging, different kinds of debugging, searching for things, recording things. They're usually not there in a way that enhances your performance. They're usually there that enhances your awareness of what's going on at the expense of performance. But when you're debugging your code, when you're starting your code, these are really helpful. And depending on what SDK you have and what device you have, there are different layers you're allowed to slip in there. There's also extensions, just like in the OpenGL sense. There are Vulkan extensions that you're allowed to include, and if you do, you put it in here. You list them in here, and then you create this logical device. So the logical device is the physical device plus layers plus extensions. So it's a little more close to what you're going to do. Now, and queues. All right, so layers and extensions. This is a list of layers that comes with the SDK, the LunarG SDK that I had loaded at the time. And this is a list of extensions that the system I was on was capable of doing, and only this one if you're on Windows. Okay? These are the ones that I think are available. They may not be the ones that actually are capable of being implemented. Okay? But they're the ones I would love to have if I can get them. The next thing you do is you ask what layers are available, and here's where you get that, is you query it here. How many layers do you have and what are they? And the same thing with the extensions. How many extensions do you have and what are they? So here's what the device is capable of doing. Here are the things I would really like. The next trick, this is what I found. These were the layers in the LunarG SDK. Here are the extensions that were available. What you do then is you ask for the layers that you actually want, and then you compare that to the layers that are available and narrow the list to only load the layers that you want and are available. Same thing with the extensions. What extensions would I like to have? What extensions are available? What's in both lists? Go ahead and load those. And so this is the code that does that. It basically looks through both lists, trying to find things in common. From that, it creates a third list, and so here's the three I wanted, or I got. And from that third list, you ask for them. So you have the ability to extend your capabilities both with the layers and with the extensions. And it's very OpenGL-ish. All right, here's the queues. We've already done that. All right, now let's talk about synchronization. Synchronization is important because Vulkan wants to run flat out. Every VK command is capable of running off on its own. Nothing blocks waiting for anything else unless you tell it to block waiting for anything else. There's three kinds of synchronization that you need to worry about, at least to worry about now: fences, events, and semaphores. And they're used in different places. They're used with different things synchronizing with other different things. So if you're synchronizing the host and the logical device doing something together, you use a fence. If you're doing things between command buffers, you use an event. And if you're doing things between queues, you do a semaphore. And these show up in interesting ways. Okay, so let's do the semaphores. The semaphore is used to control the readiness of resources between queues. To create them, you give them to a Vulkan function which sets them. Some of the semaphores you're allowed to, or some of the synchronizations, you're allowed to set yourself, and some you're requiring Vulkan to set. Some you're allowed to test yourself, and some you're requiring Vulkan to test for you. Okay? Semaphores are one of the ones you have least control over. The Vulkan function sets them, you don't end up doing any of the testing, and then the Vulkan function ends up seeing if it's done or not. So here's an example. We have a data structure called the semaphore. Here's the create information, which doesn't have much in it right now. Here I'm going to create the semaphore. And now to use it, here's an example of using it. When I'm acquiring an image to render into, I send in the name of the semaphore right there. Notice I never set it. I never set the semaphore. This function is going to set it for me. And notice I'm never asking if it's ready. This function is going to check it as part of being supplied right here. Okay? So that's completely under the control of Vulkan, although the fact that you asked for it is where your control comes in. And so we're not going to submit things to the queue until the image is ready. That's what we're asking for. Here we're acquiring the image, setting the semaphore. Here we're going to present the queue, or present the image so the user can see it, but we're not going to allow that till the semaphore has been shown. And the semaphore is linked into a pipeline stage that's the bottom of the pipeline. So essentially what we're saying is, don't allow the user to see this image until everything has passed through the pipeline. Notice what would happen if we didn't do that. Everything wants to run flat out. We would be allowed to see this image, well, anytime. And who knows what's in that image, but it's probably not completed the rendering at that point. So this is an example of synchronizing. Fences are used to synchronize the application with commands that you've submitted to the queue. It announces that the work is finished. That is, you can actually go check that yourself. It's tighter control than the semaphore. Here's an example of using it. So here we've created a fence. Here we're going to do a bunch of operations. And here we're going to wait for it. Now this blocks. This is an event. If you don't want to block and you just want to see how things are coming, you can do that up here. Just get the fence status. This is useful if you want to go off and do other work. Okay, this operation, like transferring a file from the host over to GPU memory. Okay, it's not done. I'm not going to use it. I'm going to go off and do something else. Here's what you do if you're going to use it, is you wait for it to block. Yeah. All right, events are even more fine-grained. Events can be signaled by the host or the device. You can also signal within the pipeline. This is very cool, is the pipeline can be signaling that things are happening. Remember all those stages in the pipeline, one stage could signal that things are now going through it. And this is a great way to do very fine-grained synchronization. So here's an example of controlling events from the host. We create an event. We set the event. We're allowed to, well, this is like setting the event to 1. This is like setting the event to 0. And then at any point we want, we can get the event status. Okay? The host cannot block waiting for an event. your C code can only query. What's interesting about this is the device can't test for the event, but it can block. So the host can test but not block. The GPU can block but not test. And so the way you let the GPU test for this, or use it, is you do a VK command. And so here we are in the command queue, and this is how you block up the command queue. So if you've put some commands in there and then you want the command queue to come to a grinding halt, waiting for some things to finish, this is how you do it, is you put the VK command wait events in there. Okay, so it's another form of synchronization. I think the coolest synchronization is something called pipeline barriers. And this is where you get the really fine control inside the graphics pipeline. So remember, we had all this list of commands that can be poked into the command buffer. And remember, we want them to all run flat out. Now, we could wait for every command to get to the bottom of the pipeline. By using an event, we could check for that and wait for the next one to go. But that would be wasting a lot of time. And there's no way for Vulkan to know that. There's no way for Vulkan to be able to figure out if that's what you want to have happen. So a real common example is you're having one stage of the pipeline filling up an image, that's writing to an image, and another thing, another operation is going to use that image as a texture. Okay? Now, I can use VK commands to fire off that first one. It's now running, it's rendering my Vertex buffer into an image. I can use VK command then to fire off the second one, grab this image, use it as a texture, but I'd better not. I'd better not do that because that texture image isn't complete yet. Only until that first one has gone through is the texture image complete. That's where pipeline barriers are great, because you're allowed to do things based on the pipe. It may turn out that I'm writing things from the Vertex buffer, or from the Vertex shader, waiting for another stage to use that. In that case, I'd only want to block waiting on the Vertex shader. I don't want to block waiting on the end of the pipeline. So you've got all these combinations of things that you may want to block on. This is where pipeline barriers are just so interesting. Okay, so, there's race conditions. That is, well, this is the example is I'm trying to do something right away, but the thing I'm waiting for hasn't finished yet. If I don't do a pipeline barrier, I'm going to start using it anyway, even though it's not there. All right, so how do we do this? There's this wonderful VK command called, well, pipeline barrier. And what that means is whatever VK command you did last, right before this, this blocks things in such a way that the command that comes next can't go. Okay, so it's really a 3-command sequence. One command to start something going, the pipeline barrier command to say what to wait on, and then what to happen next. Okay? Now, what goes into this pipeline barrier call are the 2 stages. And in the arguments, they call them source and destination. Really, this means whatever command was the one before, and this is the command, whatever one goes after. Stop it. Okay? They call them source and destination, but they're really the command before this one and the command that's after. And you tell it what stages you want them to block on. Or what stage this is going to trigger the block and where this one's allowed to go. So I think of this whole thing as kind of a ridiculous city streets with stoplights illustration. So here are our command we've already executed. And let's say in this operation, what we want to do is we want to allow these to get to a certain street, and the moment they get to that street, they're going to trip a sensor, which is going to tell a certain traffic light on this street to turn red. So we have two pieces of information, the sensor street and the stoplight street. And so if you want to think of it this way, this is the sensor street, this is the stoplight street. Okay, here are all the different stages that you can either trip the sensor at or set the red light at. Yeah, pipeline stages. There are different kinds of things you can stop. That's what the accesses are. But here's where it kind of gets interesting. So let's say we're doing this. Let's say we want to have the fragment shader be the trigger, be the stoplight sensor. We're not going to stop there. We're just going to use that to trigger the red light. And we're going to let the bottom of the pipeline bit be where the stoplight is. So whatever's going second, we're not going to allow it to pass there until everything has passed here. Okay? And in our stoplight diagram, it looks like this. The moment that these commands pass the fragment shader, they trigger a red light to come here. Now when we execute those commands can only get this far in the pipeline. And so depending on what you're doing and what's needed afterwards, this is how you set things up. And this is just very cool in its flexibility, I think. All right, let's see. We have like one more thing to cover. Yeah, let's just plow on through. All right, push constants. Push constants we saw before because they were part of the pipeline layout. The pipeline layout had descriptor sets and push constants, and these were things that, well, basically they got allocated as part of the pipeline structure. Okay, what are push constants? Push constants are some auxiliary information. They're a really interesting addition to Vulkan. Basically, it's some number of bytes that you're allowed to push into a specific storage location in the Vulkan pipeline. What you do with them, that's up to you. And the Vulkan spec says, at very least, you have to provide 128 bytes of push constant. The NVIDIA card I was using did 256. You can query that. Now, 128 bytes, what is that? Well, let's see. A transformation matrix is 16 floats, which is 64 bytes, which is 2 matrices worth of space in a push constant. That's the kind of thing you'd use it for. What it's used for is for some things that you want to change very quickly, but don't want to have to rebind a new pipeline or send new information in a descriptor set. It's sort of a cheat. You know, in some ways, I would, if I had been chosen to name this, I would have called it a cheat constant, because it's this funny cheating path down into some empty storage in the pipeline structure. But it's neat, because if you need to do a lot of things really fast, it's the way to go, because you don't have to go through the laborious process of just swapping out descriptor sets or swapping out pipelines. So now, how do you get at it? Okay, well, how you get at it is in the shader, in the layout, you put the word push under bar constant. And so here we've got push under bar constant, and it's a mat4. So this is a good example of, I want to change the model matrix really quickly. Render, change the matrix. Render, change the matrix. Render, change the matrix. This is how I'll do it. And the model matrix is in the push constant, and all I have to do is keep pushing across different bits. And that's why it's called a push constant. you're pushing across different bits. And here's how you do it. Command push constants. You give it the layout structure where that belongs, what stages to use it for, the size of what you're sending across, and a pointer to the values. And because it's a CMD, it goes in those commands. So you do command render, command push constant, command render, command push constant. Okay. Yeah, and so this was back from the pipeline layout. We had looked at the descriptor set where it went. Now we fill this in. That's where the push constants go. As far as this goes, it looks like it's here. Really, it's sneaking down, but where it fits, where we see it in the structures is up there. So this was an example I did, and I forgot to bring the video to play, but you can imagine what it looks like. Imagine if we've got a robot arm. If I'm going to change this angle, or change this angle, or change this angle. And if I change this angle, all three links in the arm move. Okay, it's like moving your shoulder muscle. All these other links move. If I change this angle, just the red and the blue pieces move. That's like your elbow. And if I change this angle, just the blue piece moves. And so what do I want to do? What I want to do is very quickly either get angles or get matrices down into what I'm drawing. And I could do angles, but angles don't get you movement. Matrices do. So the code that you'll see, it's using the C program to compute the matrices and then sending those down as push constants. So it's sending this matrix down and then drawing the green piece, sending this one down, drawing the red piece, sending this matrix down, drawing the blue piece. All the matrices are going down with push constants. So here's setting up the matrices. Here we're telling it about the pipeline. Yeah, so exactly what we said. Push constants, draw. Push constants, draw. Push constants, draw. At this point, we're done. We didn't have to rebind anything. So that's why I'm so big on, I like push constants. I wish they had a little more space because there's more I want to do with them. All right, there are some more things in the notes, but I imagine you all are pretty sick of Vulkan by now. Let me just show you what's there. Anti-aliasing and multi-sampling. Vulkan has a way of dividing each pixel up into multiple pieces. It's got two different ways of rendering into it, so that if I've got this red and blue polygon, that pixel is not going to be red, it's not going to be blue, it's going to be magenta-ish, because each one has a different coverage. It does it basically the same way OpenGL does it, multi-sampling and super sampling. Okay, and there's here in the notes, but again, I kind of sense everyone's getting tired. And then there's also multi-pass rendering. And this is one of the cool things you can do with multi-threading. You know, and we'll end multi-pass too. Like, say that we're doing something where the first render is going to generate a color buffer and a depth buffer, and the second render is going to use the depth buffer for something, and it's going to pass out more depth, and maybe the third render is going to use colors and these depths, and finally do the frame buffer. This happens a lot in like gbuffer type algorithms. This diagram is really the key to the whole thing. If I was putting together this as a graph structure in a computer science data structures course, you would know how to do that. You would say, oh, this points to this, points to this, points to this, points to this, points to this. There's my graph. If you think of it that way, that totally explains the kind of code you use to set this up. Is you basically have data and you have render passes. And so render passes generate data which go into other render passes. So again, there's sample code here. All right, so if you've got questions on anything or the things I just blew through because I know you're tired, come on up afterwards. Or if you just want to chat, come on up afterwards. I'll stick around as long as you're here. Again, this is the website where all of my Vulkan stuff is, which includes all the notes. Up at the top, there's a Hey SIGGraphers section, and that's got the notes all put together like we saw here. For the university class, I had them broken up into sections, and all of those are down below. So if you just want to see push constants, you don't have to wade through this. There's a zip file with all of that code and all the files in it. There are some of the files broken out, like the CPP file is broken out. So up at the top where it says, Hey SIGGraphers, there's a bunch of stuff there. But if you go to that web page, you'll find that. There's my email address. If you've got questions, comments, anything, I would love to hear from you. This is an adventure we're all in together. Thank you.